We now proceed to example 4 involving a roller cam bicycle brake. A common challenge in engineering is designing a component to withstand repeated or extreme loading. Here we have a prototype of a roller cam bicycle brake that is exhibiting failure in member ABC as well as its mirror element on the other side. As an engineer, your job might be to figure out why the prototype is failing and make suggested design modifications to make a more robust component. We can get a basic idea of the functionality from both the schematic and the perspective view shown in this slide. As the rider squeezes the brake handle, the cable at D is pulled upward. The cam is a single rigid body undergoing pure translation, so these surfaces likely try to move upward, and as they do, they push the rollers out in these directions, affecting rotation about the bolted connections this way, therefore causing the brake pads to squeeze the wheel rim and bring the bicycle to a stop. For a given input tension T, we'd like to know the squeezing force P. So what is P as a multiplier on T? To keep the analysis two-dimensional, we'll neglect friction between the brake pad and wheel rim. This may be a critical omission, however, so we'll come back to it after we've examined the brake in 2D. What value should we use for T? The value of P will be obtained as a multiplier on T from the equilibrium equations that follow from a free body diagram of ABC. Assuming that failure follows from extreme loading, we should use a value for T that corresponds to the maximum force that a person could possibly apply to the brake. Recalling example 2 from section 5.3, the maximum force that a rider could reasonably exert is on the order of 100 pounds, corresponding to 450 newtons. In order to avoid confusion with our initial figure showing the rim squeezing force as P, let's call the rider's hand force Q in this figure. With Q equal to 450 newtons, we could perform a variety of analyses on this handbrake. In section 5.3, we did so with a certain value for the spring constant, CD. To get a more extreme value for the relationship between T and Q, we could remove this spring and perform the analysis again. In doing so, we would then find that for Q equals 450 newtons, our analysis gives us T equals 723 newtons. This is a larger multiplier for T as a multiple of Q than we would have found in the analysis for section 5.3. Let's take T to be equal to 750 newtons to have a more round number. Now let's generate free body diagrams of the cam and member ABC. We'll begin by drawing enveloping surfaces to isolate the cam as well as the member ABC with the roller in contact with the cam. So here are our enveloping surfaces that will form the basis for our free body diagrams. 1 for the cam and 2 for member ABC. our contact with the rollers are making these angles of 55 degrees with the horizontal. We'll neglect any friction that occurs between the roller and the cam. And so the contact forces here will be symmetric on both sides, and we'll call these forces N here and here. With this angle being 55 degrees here, this angle is also 55 degrees, and that means that this angle will be 35 degrees here and here. The symmetry of this arrangement means that the forces that we have acting on this body are concurrent. If I've drawn them correctly, they should all intersect in the middle here, which means we have a concurrent force system, and the cam is automatically in moment equilibrium or in rotational equilibrium. In addition, the symmetry of this object is such that we don't have to worry about force equilibrium in the x direction. We can see that we're just going to have n cosine 35 minus n cosine 35 is identically 0. So the only equilibrium equation we have yet to employ here is simply vertical equilibrium. For arm ABC, we have something like this. And we have equal and opposite forces N here. So we have a force N here. Again, that also is going to make an angle of 35 degrees with the horizontal. We've got bearing forces Bx and By here. And we've got our force P pushing back on the brake pad here. For the equilibrium equations for free body diagram 1, all we have to do is enforce vertical equilibrium. Sum of the forces in y equals 0. That gives us T minus 2n sine 35 degrees is 0, which gives us n is equal to T over 2 sine 35 degrees. For our second free body diagram, we can begin by taking moments about B and setting that equal to 0. Here it will help to break up our normal force N into its horizontal and vertical components. In this case, both components are exerting positive moments about B, and the force on the brake pad P is exerting a negative moment. We can see from the geometry of the figure that our moment arms are going to be for the horizontal force N cosine 35 degrees. Our moment arm is going to be 50 millimeters. And for the vertical force of N sine 35 degrees, our moment arm is going to be 25 millimeters. And then for the brake force P, or the force on the brake pad P, the moment arm is going to be 35 millimeters, and again its contribution is negative. So we can rearrange this for P in terms of N first, and then use our expression for N in terms of T to get our multiplier that tells us the relationship between tension T and brake pad force P. So first, from this equation, we'll pull the N out, and we end up with cosine 35 degrees times a ratio of 50 to 35 plus sine 35 degrees times a ratio of 25 to 35. And then if we make our substitution for N in terms of T and bring the 2 sine 35 in the denominator inside the parentheses, what we end up with is 1 over tangent 35 degrees times a ratio of 25 to 35 plus 25 over 70. And that number in parentheses turns out to be 1.377 T. So that gives us the amplifying factor between the input tension and the force on the brake pad at P. We can continue our analysis by figuring out what the bearing forces are, Bx and By. Force equilibrium in X gives us Bx minus n cosine 35 minus P is equal to 0. And now having n and P as multipliers on T, we can get a similar expression for Bx using our result that n was T times 1 over 2 sine 35. We end up with 1 over 2 tangent 35. And then our value of P was 1.377 times T, and this ends up giving us 2.091 times T. In the vertical direction, we had n sine 35 minus By is 0, and that gives us By equals T over 2, or 0.5 T. This gives us the orientation of the bearing force at B, because it tells us that we've got roughly a 4-to-1 ratio between the horizontal and vertical components. So over here, we are going to make this very shallow angle bearing force. Here will be the resultant. And in fact, we can calculate what this angle alpha is here for the resultant bearing force. That value of alpha will be the arc tangent of 0.5 over 2.091, and that ends up being 13.4 degrees. Now, how do we determine if these forces are excessive and perhaps responsible for the observed failures? We really need to know where and how ABC is failing to make a more educated guess of what is responsible for the failure. Our present 2D analysis has given us the forces on ABC as multiples of T. We will see in Chapter 8 that internal loads, forces, and moments develop in these bodies as a result of such loads. If these are the loads responsible for failure, we should look for failure related to what we're going to call bending moments, although that's a term that may not be familiar to you yet, at certain locations related to peak bending moments. So for instance, it will turn out that if we have an excessive force here, the normal force turns out to be excessive, then we're going to end up with a peak bending moment right down here on the side above B. And if the force P down here is excessive, it's going to tend to exert a peak bending moment right here on the side of B. So when I say that it's on the side of B, we're looking at a perspective view here from the front, and we'd really have to look at this on the sides. So if I were to go back to my original perspective view, and we'll do that shortly, we'll be able to get another view of where this failure would occur. Now, if the problem is with the excessive bearing force, then what we might look like is a failure on the side over here around bearing B. So these would be three locations that we might look at in order to determine if it's these planar forces that are giving us a problem. And when I say that these are occurring on the sides, what I mean for the bearing force here is that it might be occurring somewhere in this region here if this is excessive. And even though it's in the background here, if I were to go on the other side here, this is where we might have excessive bending forces from the contact here. And again, it's going to be hard to see here because it's being in the background, but if I were to go on the lower side here of the brake pad, if this force here is too large, then these might be the locations where I would look for a problem. Now, what other possibility is there? We said initially that we should neglect friction with the wheel rim. How would that change the problem, and where would the location of failure shift due to these new loads? So I'm going to again attempt to sketch my arm ABC here. And we've already got our value of the contact force N here. And we have our bearing forces Bx and By. And our brake pad force P. Now to fill in the rest of this, I'm going to sketch the wheel rim over here. And it's important to realize that if we're looking at this forward, so what I've sketched here would essentially be the wheel rim in here. And if this is coming forward, then a velocity vector for the wheel at the top here would be coming out of the plane of the figure at us. The nature of friction is always to oppose this motion, so the friction force on the wheel rim would go in the opposite direction. That is, it would be going into the plane. But we have an equal and opposite force on the brake pad, and so that would look like this. That is, the wheel coming forward would be trying to drag the brake pad towards us in the plane of this figure. Now this is going to be reacted at our bearing B, and so in addition to the forces Bx and By, we're going to have an axial force on this bolted member, which is going to be into the figure. So this is also F, corresponding to this X. But then in addition to that, the fact that this arm is trying to be pulled forward is going to require the bolt to sustain a bending moment perpendicular to the axis of its fastener. So we know that the bolted member can allow rotation in the XY plane that we can see here, but it certainly cannot allow rotations within the plane. So there's going to be a bending moment here this way that's also responsible for this reaction. And what will happen in this case is that we'll tend to get a peak location for the bending moment, which is now on the top segment right here. So now we should be able to actually see this. So as opposed to the other locations which were on the sides as a result of the planar loads, these out of plane loadings would tend to produce peak stresses and induce failures at the location that we've shown in blue here. The point of this is that by considering our analysis with the observed location of failure, we can develop hypotheses for the root cause of the failure and redesign the component to reduce or eliminate the problem.